Hello everyone, this is our mini video or lesson recording for 1.07, which is the first part of reasoning. And we're going to just kind of take it slow digging into reasoning, but we're going to talk about inductive and deductive reasoning, and then also truth value and counter examples. Okay, so let's first start out with reasoning. And even though, like, you've kind of probably been noticing in geometry that a lot of the stuff that we've covered, it's just common sense things or things that you do every day. It's just putting a name with them. So you do inductive reasoning and deductive reasoning every single day. Your parents do it. Your grandma, grandpa, brother, sister, family, friends, everybody does it. I do it. Principal, we all do it. Okay? You just probably don't know what it's called. Okay? So what is the difference between these and how can we use them? So inductive reasoning it's a type of reasoning that's based on observations found in patterns, okay? So it's when you come up with an idea or a conclusion, okay, you are basing your conclusion on observations, patterns, and past events, okay? You use inductive reasoning to kind of draw a general conclusion, okay? Just one in like, I've noticed that this happens a lot, so it must be this, blah, 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 okay? You can form a conjecture or an idea, which then must be proven, okay? So inductive is at the beginning, and it helps us form the ideas. You do not use it in proofs, and we're going to talk about what proofs are, but you don't use it to defend something or to justify it. You use inductive reasoning to direct you in the direction of where you're going, okay? Deductive, so we've got inductive and then we have deductive. Deductive is a type of reasoning that uses previously proven or accepted properties to reach conclusions. It follows D rules, like definitions, things that we know for sure. We can say, oh yes, those are parallel lines because they are lines that go in the same direction and they don't intersect, okay? Your inductive reasoning would say, I think they're parallel because look at them here. They don't intersect. I think they're parallel, but then you would use deductive reasoning to prove it, okay? Deductive reasoning can draw a specific conclusion from general observations. But then it's used to prove conjectures. Once proven, they become theorems, which can be used to prove future conjectures. So let's look at what I'm talking about. Let's look at some examples, okay? As a reminder, inductive is like your gut instinct on things, your gut instinct. And then deductive is solid evidence, okay? So it says, since the lowest grade in history on any assignment or test is 92, you conclude that your average grade in history class is 92 or above. Now, your gut instinct might have helped you that, but can you prove it? Does it have solid evidence? Does it have solid evidence to back it up, to back up your conclusion that your grade's going to be 92 or above? Yes, we have solid evidence because all of your grades so far have been a 92 or above. So your average has to be. So because we have solid evidence, this would be deductive reasoning, okay? Deductive reasoning. Now, let's look at another example. Bob, the big bad boxer, has won his last 11 matches in less than 5 rounds. So he beats everybody pretty fast. You conclude that he'll win his next match in less than 5 rounds. Now, you have observed this not because there's a definition that says Bob, the big bad boxer, wins this. There's not a definition that says how fast Bob bad boxer is, or big bad boxer is. Okay? There's no definition. There's no rule. There's no law. What if he's hurt that day? What if he doesn't feel good that day? He may not be as good as he normally is, right? So we concluded that he'd win his next match in less than 5 rounds based on past experiences, okay, or our gut instinct. So this is inductive. We don't know for sure if he will continue the same pattern, Okay? We are basing it on patterns, but we don't know for sure. Okay? It's kind of like, hey, Texas weather is a prime example. It's, the end of August. I'm going to bet that today's going to be hot because we live in Texas. Now, does that mean it has to be? Absolutely not. Something crazy could happen. We never know with Texas weather. But my inductive reasoning, my gut instinct is telling me it's the end of August. It's going to be hot tomorrow. Okay? Now, deductive reasoning is the cornerstone of mathematics. So without it, we would never be able to make general statements that we know are always true. Okay? So when you use deductive reasoning, you're using the proven theorems. You're using the definitions. You are drawing conclusions based on information we know to be true, okay? Deductive reasoning is used in mathematical proofs. So whenever you go through your lesson, you'll learn about what a proof is, okay? It is the valid way to draw conclusions in mathematics. So it would be like also outside of mathematics, it'd be like if you went to court, like a lawyer, okay? A lawyer's going to use solid evidence, fingerprints, surveillance cameras, eyewitnesses, right? He's not going to say, oh yeah, I think it is this guy over here because he's robbed a bunch of jewelry stores before, okay? You can't say, oh yeah, I think it's him because he's done it before. You have to have the evidence to blame him, okay? So deductive reasoning, it has solid evidence. Inductive is your gut instinct. So a lawyer or a detective might use inductive reasoning. They might say, you know what? I think that we might need to go look into so-and-so because he's done this before and he was in the area at the time. So your inductive reasoning can guide you or direct you in one direction, but your deductive reasoning is what we use to prove it true, okay? Now, when we come up with these ideas, these are called conjectures. It's an educated guess or a theorem that's yet to be proven. So when we determine this pattern here, okay? When we want to determine what the next number is, we would look at it and say, okay, well, based on what's happening here, between 1 and 4, it has a difference of 3. 4 and 9 has a difference of 5. And then 9 and 16 have a difference of 7. So these are increasing. These numbers are increasing by 2 each time, right? So the difference to this next number is going to be plus 9. So 16 plus 9 would get me 25. So our conjecture is getting that number, but our reasoning would be deductive reasoning by looking at the numbers, looking at the pattern and proving that this is the pattern, this is what's happening every time. This conjecture here, after observing this pattern, what would be the interior angle sum for an octagon? Now, just looking at this, we're like, okay, a triangle, quadrilateral. So the number sides is going up by 1 each time. Okay, and I want to know how much the interior angle sum is for an octagon. So if I look here, 180 to 360, 360 to 540. Well, these have a difference of 180. These have a difference of 180. So I'm thinking that every time these are going to go up by 180. So 900 plus 180 gets me 1080. So I'm using those patterns to come up with a conjecture. After observing this pattern, how many dots will be in the next set? Okay, let's look at what they're increasing by. This went up by 2. This group went up by 3. This group went up by 4. This group went up by 5. So I'm thinking that this next group is going to go up by 6. So 15 plus 6 gets me 21. Now for counter examples. So to prove that a conjecture is true, you need to prove it true in all cases. It can't be true sometimes or all but a few times. It has to be true all the time, okay? To prove that a conjecture is false, you need to provide only one single counterexample. And a counterexample is an example that shows a statement is not always true, okay? So to prove it true, it has to happen all the time. To prove it false, you just need one time it did not happen, or one time it was not true, and that makes your statement false, okay? So a counterexample is when we prove that something is not true. So let's look at this example here. Show the conjecture is false by finding a counterexample. So we just need one instance, okay, where our conjecture is not true. So test different numbers. So where you're given that A plus B, so we're going to pick a number for A and number for B. When we add them together, okay, we want them to be greater than or equal to 12. And we also want A to be greater than or equal to 4. Our conjecture, we know that this is true here, okay? We're given that information. And our conjecture is that B will be less than or equal to 12. So let's test out this first set of numbers. They're going to pick A is 4, B is 12. Okay, so when we add A plus B, which is 4 plus 12, it equals 16. Hey, we're good with that. We want it to be greater than or equal to 12. So that worked, right? So let's test it. It fits our given information, but let's test our conjecture. All right, that worked for that instance. A is 7.2. Sorry. B is 12. Okay. When we add 7.2 plus 5, we get 12.2. We're good with that. We want it to be greater than or equal to 12. Okay, so we're good. So these two examples of picking a 4 and a 12, that worked. A 7.2 and a 5, that worked. Okay, now does that mean it's going to work for every single time? No, it just worked for these two sets of numbers. Let's look at this one where A is 17, B is 13. Hey, let's see here. A is greater than or equal to 4. That's what we wanted to happen, right? But when you do A plus B, 17 plus 13, that's true. But B is not less than or equal to 12. So it did not work. So what our conjecture said was that if this stuff is true here at the given, B will always be less than or equal to 12. But for this example, our two numbers, it fit this information here at the beginning, the given. However, B was not less than 12. So that one example, I don't need to come up with any more. That one example tells me that my conjecture is false. Okay, and all I need is one counterexample. Okay, let's look at this one. So it's determine if the statement below is true or false. If false, then provide a counterexample. It says, for any integer n cubed is positive. Now, I would, if you're not sure, and I understand because, hey, listen, I've taught math for a long time. I've been doing math for a long time, but I still, from time to time, need to look up the definition of what an integer is. That's okay. That is okay. Go look up the definition of an integer if you need to, okay? Integers do include negative numbers and positive numbers, okay? So that would be a good place to start. So if I do, let's just pick a 2. So 2 cubed would be 2 times 2 times 2, right? That's an 8. Okay, cool. That's positive. It worked. Okay, let's do a negative 2. So negative 2 cubed would be negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2, that's a 4, because remember, two negatives make a positive. but then 4 times -2 ends up being -8. So, can I say that this is true? Can I say that this is true? No, I can't, because there was one instance, and that's all I need, one instance to show that this is not true all the time. So this would be false. Okay, we got one more counterexample, or one more example. Determine if the statement below is true or false. If false, then provide a counterexample. Okay, so 2 complementary angles are congruent. Now, in case you missed a lesson on Friday, or you might just not remember, that's okay. You can Google what complementary numbers are. I'll go ahead and tell you, though. Complementary numbers are two or more angles that add up to 90 degrees. Okay, so they have a sum of 90 degrees. That could be 45, a 45-degree angle plus 45-degree angle. Hey, those are congruent, right? Those are congruent, and they add up to 90 degrees. Well, cool. Okay, but what about this? What if I had 50 degrees plus 40 degrees? These are complementary angles because they add up to 90 degrees, but they are not congruent. A 50-degree angle and a 40-degree angle are not congruent. So that, just one counterexample, one time. I don't even need to do any more. There's plenty more, but I don't need to do more. I just need one counterexample. So this is false. Okay, guys, make sure that you're going through that lesson. There's lots of definitions, a lot more examples over inductive, deductive reasoning, and also counterexamples. So please make sure that you're going through that. We'll talk more in class, but if you have any questions, please make sure you reach out to your teacher. Thanks, guys.